Hello. Today we're going to talk about the shell method. Last time we talked about the disk method, which was a way of finding volume using disks on top of each other, or I guess side to side, in the same direction. And this time we're going to talk about the shell method, which is more like concentric tubes or circles, cylinders. So if you thought about a whole bunch of pipes of slightly different sizes that were all concentric and fit into each other, that would be similar to what we're doing this time. So again, like last time, instead of really explaining it to you, I'm just going to jump in and do a problem. And yeah, we'll do it. So the important part with these is not so much the memorizing the formula, but just getting an idea of kind of what's going on, the feel for something. We're taking a 2D object. In this case, it's going to be a circle or a cylinder, and we're going to add some volume to it using delta x or delta y or delta variable of integration. So we have y equals square root of x and y equals x, and we are going to revolve such about the y-axis. So let's see here. This will be y equals x. And y equals square root of x will look something like this. And it'll be from 0 to 1. And the between 0 and 1, square root of x, x to the 1/2, will be bigger than y equals x. The way I remember that is, back in college, we would joke that you would be in the square root club if you took your GPA and square rooted it and it actually got bigger. It's not an enviable position. Okay, so we have a figure like this with the area bounded as such, and we're going to revolve it about the y-axis. So it's going to look something like that. Again, not drawn to scale. Like so. And then maybe kind of like so. Okay, and so the idea, that is not a pretty picture. So the idea with the shell method is we're going to take this section right here. I'm going to do a cylinder into just 3D shape, and then that's going to give us the volume of this area, and then we're going to subtract off the cylinder from this area, where the thickness is delta x, because we're going to integrate in this direction, and then we're going to know that the top part of the graph will be y equals x to the 1/2, and then the bottom will be y equals x. So if we write this out, we'll write it as, so we're going to integrate from 0 to 1, and you might be thinking, well, wait a second, we got a whole bunch of the shape over here. Why don't we integrate from -1 to 1? Well, we're integrating along the radius. So we'll be doing from 0, 1 to, let's see, a cylinder is, what is it, 2 pi r? Yeah, I'm going to say 2 pi r. The area around a cylinder is 2 pi r, and then we'll multiply it by a height. I'm going to call this height big for the top one. And then we're going to multiply it by dx, delta x. So what this 2 pi r does is it gives us a circle like this. The h gives us a height to the cylinder, and then the delta x gives us a thickness, which will then be able to give us a volume. And one of your objections might be, well, the inside radius is different than the outside radius for this, and they differ specifically by delta x, and so you can't really say it's 2 pi r. That's true, but as delta x gets infinitely small, the difference gets infinitely small. And so we're infinitely close to the correct answer, which is pretty much the correct answer. So what this does right here is it gives us the volume of the top cylinder, and then we're going to subtract off the bottom cylinder, which is this part right here, and we'll have 2 pi r. I'm going to call that then h small. H is the height of the small cylinder, and then we're going to multiply by delta x as well. Okay, and then to simplify this, we're going to, since the 2 pi's will be the same, and we can then combine the two integrands, because they have the same limits of integration and the same delta x. So we'd have 2 pi, let's see here, r will equal x, because as we're moving along from 0 to 1, whatever the x value is will be the radius. HB, which will be the big height, will be square root of x, so x to the 1/2. And then height small will equal x. So 2 pi, 0 to 1. Do I want to do it that way? Nah, not yet. So I'll do 0 to 1, 2 pi, and then we'll do x to the 1/2 minus x, and then I'll change the delta x to dx. So what this is doing here, wait a second, did I forget an x? Oh, I did, and then multiply by x. So what this is doing here then is it's giving us, so if I redraw our shape real quick, we got something like this, and then there's an interior like so. And say we're at, this is the x-axis, and say we're looking at this delta x right here. So what that would give us then is, since this is rotated around and it's a 3D shape, this would give us this cylinder right there. And then whatever x is over here, this would be the negative x side. And so we're finding the volume of this little tube cylinder, if you will. And the reason it doesn't go all the way down to the bottom is because we subtracted off the height of the small cylinder. So at this point, we're just going to brute force calculate it out. So this would give us 0 to 1. Let's do a 2 pi. We'll do an x to the 3/2 minus x squared dx. Integrate powers activate. 5 over 5/2, 2/5 power rule minus x3 over 3. Integrate from 0 to 1 is this 2 pi. And then we'll have, when we plug in 1, we'll get 1 to the 5/2 is 1. So we'll be left with 2/5 minus 1/3, which is 2 pi, and then this will be, what is it, 3 times 5, or 3 times 2 is 6, minus 5 times 1, which is 5 over 15. This becomes 1, and so we're left with 2 pi over 15. Okay, that seems reasonable. And then your other thought might have been, well, wait a sec. Could we have used the disk method here? Why did we have to learn this entirely new method just to solve this? You're correct. A lot of times you can use both the disk method or the shell method. I prefer the disk method generally, just because I tend to get, it feels more intuitive to slice things up instead of concentric circles, and I tend to get less confused. But sometimes, because the disk method has a pi r squared, sometimes it's easier to do the shell method than the disk method. And you'll find a lot of times if you are revolving around one axis, in this case the y-axis, but you decide to integrate along the x-axis, then you're probably going to do the shell method. It's just going to naturally fall out that way. Same if you revolve around the x-axis, but you decide to integrate along the y-axis for whatever reason, then you're also going to be using the shell method. So I'm going to redo this problem real quick, but this time I'm going to do it with the disk method. Ideally, I'll go a little bit quicker because we already went over the disk method. I'm here to show you the shell method, and I should be pretty fluent at this. One would assume. Okay, so we have this shape, and we're doing the disk method. So, orange. So we'll do this. Here's our delta y. Y equals x, right there. And then y equals x to the 1/2. But since we're going to integrate along the y, we're going to want y squared equals x as the interior. And so we are going to subtract the big minus the small. So we'll go from 0 here up to 1. So we'll go 0 to 1 of pi r squared. So we'll do r big squared minus pi r small squared delta y. And r big equals x, y, no. R small equals y squared. Okay? Yep, that makes sense. Between 0 and 1, y squared is smaller than y. Factor out of pi, and then we have r big, yep, y squared minus y to the 4th dy equals pi, and we'll do y cubed over 3 minus y to the 5th over 5, 0 to 1. Okay, we got this. Go team. Go team. So we have 1/3 minus 1/5. This should be angle brackets. Pi 5/15 minus 3/15. Yeah, this is gonna work. This is gonna work. I'm glad this is gonna work, because otherwise I would have looked very dumb. All right, so there we go. If we use the disk method, going from 0 to 1 for in the y direction, we got 2 pi over 15, which is the same thing we got doing the shell method. So I could have just been wrong twice and coincidentally everything matched up, which, I guess 2 wrongs do make a right sometimes. But I assure you it's not the case this time, that we're actually just correct both times. Though if you do make a sign error, try to make it in even numbers of sign errors. Okay. Hop hop. Kapow. Do one more example just to make sure we get the concept. And you can do any sort of shape when you're trying to integrate. It's just that shells and disks are going to come up more often than everything else. More convenient in life. Okay, so we got y equals 4x and y equals x cubed. That's bigger numbers than I feel comfortable with in life. I feel so weak. Like, 4 x cubed, that's outrageously big. Okay, so I should probably find out what these equal each other, since I can't just assume it's 1. So we have 4x equals x cubed, which means that 4 equals x squared, which means that 4 equals 2, plus or minus 2. No, 4 doesn't equal 2 at all. X equals 2. Outrageous. Outrageous. Okay, so we have y equals 4 times 2, which is 8. So we have the point 2, 8. So I'll draw another line there. That'll be 8. That'll be 4. And get rid of that extra little. There's probably going to be something that looks like this. And then is it smaller or bigger? So if we look at 1, y cubed is 1. So we know we have the point y equals 1 down here. So y equals x cubed is going to be on the bottom. There we go. So similar shape to what we had last time. And then we'll have something similar over here, since we revolve it about the y-axis. And then we have a circle, and we're trying to find this area in the middle, where this is y equals 4x, and the bottom will be y equals x cubed. Okay? So we're going to integrate this direction, since we're doing the shell method, away from 0 to 2. And shell is a circle, 2 pi r. And then we're going to do times height big minus 2 pi r height small. I guess I could have already just factored out the 2 pi r there. Okay, we know that r is going to equal x. Height big, we've determined, is 4x. And height small, we decided, is x cubed. So we'll have 2 pi, which we can factor out. We'll have an x, which we can factor out of both of the heights, but we can't bring it outside the integral because we're going to be integrating by x, and x is specifically not a constant. 4x minus x cubed, okay? Ooh. Delta x, which I think write as dx down here, okay? And then factoring through a little bit, we got 4x squared minus x to the fourth dx. Ooh, that's a very fancy delta x. Which gives us then 4x cubed over 3 minus x to the fifth over 5 times 2 pi, 0 to 2. The 0 is just going to go to 0, so I'll just worry about the 2's. And so we have 2 pi 4, let's see, 2 to the third is 8, minus, x, I think it's 32. So 2 to the fifth, so if we know third is 8, 16, 32, yep. 32 over 5 over 3. Feels like there should be something easy here. Okay, multiply this one by 5, so I've got 2 pi times 5 times 32, 4 times 8, over 15, minus 32 times 3 times 15. So let's see here, I can do 2 pi, factor out the 32, 32 times 2, which is 5 times 3, over 15. That's 64, 64 is 128, 128 over 15 pi. I wonder how many pi that is. So let's see, there's 15 goes into 30 twice. I don't know, like 8, 24, 8 pi maybe? That's a good amount of pi. Okay, so the idea here is, I know that felt kind of abstract. The key part of this that we did was right here. So when we're doing the shell method, what we're going to be doing is making cylinders. The way you make a cylinder is 2 pi r for the circle of the cylinder. You then add some height. I usually call this h big. And then we might want to take a little bit off, so we'll make another cylinder. 2 pi r, same radius, height small. And that gives us our cylinder. And then gives us a smaller cylinder, which we want to get rid of. And then to add some volume to this, we multiply by delta x. And we integrate over from the middle usually outwards, and then that will give us our total volume of a revolved solid. And again, it's best not to try to force memorize these equations or the specific steps. The idea is you're making a shape, you're using part of the shape as a delta x, a small increment, and you're integrating that along an axis. And so if you can break down the shape of whatever you're looking at into small sections, you can then integrate across all the sections. And that's the key concept we're going on this one. And that does it for the shell method. What we'll be talking about next time will be line integrals, so finding the length of a curve. So that should be it for volume, more or less. Appreciate it. Thank you much.